different issues concerning the usage of the strain gauges. Yesterday we saw something concerning the transfer sensitivity of strain gauges. Now let's see what happens if we are working in a temperature field that is not the one that is expected, that is designed to operate. What does it mean that? It means that we are operating the strain gauges at whatever temperature. So there is no temperature reference but the one that the manufacturer is telling you. Okay, so I could be in a reference operating temperature equal to, let's say, 100 degrees, okay, if my strain gauge manufacturer is telling me so. Okay, so no melting water temperature, no boiling water temperature as reference one. Please remember you have to refer to the manufacturers for their operating reference temperature. That's because we can use strain gauges to measure the strain of a structure when it is operating at very high temperature. For example, the case of an operating engine, jet engine, okay? Or we can have the need to measure the strain of a structure operating at very high level of flight, let's say 10,000 feet, 10,000 meter high. So temperature is very, very low. So because of the non-linearity, as we can see in a few minutes, of the behavior of the strain gauge with respect to temperature, it is very important that you know very well what is the reference temperature. Having said that, let's see what are these effects. So let me talk about temperature effects when operating, of course, strain gauges. Remember, we had a very important equation that is characterizing your strain gauge working principle. And that equation is that the relative change of the resistance is due to the strain, okay, just by following that equation, which K, once again, is the strain gauge factor. It could be global or just strain gauge, according whether or not we are considering the transfer sensitivity effect, okay? K is the gauge factor. Typical value is 2, okay? Remember what I told you yesterday, and remember the new information that you have to input in your DNA code, okay? So when referring to the effects of the operating temperature to our, let's say, measuring circuit, to our strain gauge, we have to consider 3 different effects. The first one is the effect that is linked to the change of the strain gauge factor with the change of operating temperature. So we have to consider that K is a function, or let me call that the change of T, temperature, with respect to the reference one. Okay. The second effect that has to be considered is that also the resistance is changing because we are changing the operating temperature. So we have to consider that also the change of resistance is another function of the change of the operating temperature, so delta T. And finally, 3 is the strain. Remember, the strain is characterizing the operating conditions of your host structure, the unknown quantity, if you will. So also the strain, because of the linear coefficient of the thermal expansion, is subjected to the different operating temperature. So also the strain is another different time function of the operating temperature, so delta T. Okay, now let's see what are these 3 different effects, one after the other, and then at the end we put them together in order to have the overall evaluation of the effects of the operating temperature to your strain gauge measurement. So let's start with the first one. Okay, so first effect is that the temperature is affecting the value of your strain gauge factor. As a matter of fact, this change is not that easy to characterize. However, what we can say is that from experimental analysis, there is a very well-known trend, okay, that is giving me the information, this change of the strain gauge factor as operating temperature is changing. So in order to characterize that, we are generally using a plot of this shape in which we are reporting in the y-axis the temperature, let's say Celsius, and in the y-axis we are reporting the change, the relative change of the strain gauge factor, for example, in percentage. Okay, let's assume to have, for example, a reference temperature, let me call that T0, for example, equal to 25 degrees. Okay, of course, 25 degrees is given me by the manufacturer, so actually it could be whatever. Okay, and for that value, of course, there is no change at all of the strain gauge factor. What we can see, generally speaking, is that by changing the temperature, we are having sort of behavior that is of this shape. For example, we have something like this. Or something like that. Okay, this one is referring to Karma, what is called Karma alloy, that is one of material that is used to manufacture the strain gauge, and the other one is, for example, Costantana. And the change, so the variation of this strain gauge factor is not that much. Here we are having plus 1 and negative 1 bounding. And the temperature ranges are of about 150. Here you can go down a little bit to negative 50. Okay, let's say negative 50, no more than that. Okay, so as we can see from this plot that comes from an experimental result, we are having that the temperature is affecting the value of the strain gauge factor K. However, the change of this strain gauge factor is limited between plus minus 1% approximately. Okay, in a frequency range, okay, that is about plus minus 100 degrees Celsius, okay, around the reference temperature, here set as 25 degrees, okay. According to the different material, what we are having is that the change, the rate of change could be either positive or negative. As we can see, the Costantana material has a positive trend, the slope is a positive one. On the contrary, the Karma material is having a negative slope. So according to the different material, we can have an increase or a decrease of the strain gauge factor. Okay, because this trend is a experimental one, what is needed is that you as a manufacturer are called to characterize this trend. And for example, by assuming that those trends, those two trends are, let's say, first approximation, linear one, what we can say is that the K, the strain gauge factor function of the temperature, could be written as the K0, that is the strain gauge factor at the reference temperature, T0, times, for example, 1 plus beta T negative T0. As you can see, we are having a linear function of the change of temperature, delta T, and beta, that is telling you what is the slope, is found from experimental investigation. And by referring to the plot that I drew just before, beta could be either positive value or negative value according to the different material that we are using. Yeah, beta is the slope in our analysis. Okay. Is that clear? So please remember, and this is must be well understood, that there is no a priori defined K0, okay? K0 is the reference strain gauge factor corresponding to the reference temperature. So this pair of numbers, K0 and T0, must go together. And you, as manufacturer, has to be very clear in specifying these two values. Okay? Why that? Because if you are changing the temperature range, let's say if you are going to higher temperature or very low temperature with respect to the one that I just draw in the plot, then you can have completely different behaviors. Okay? And therefore you have to be sure to characterize your operating condition at the temperature that are close to the reference one. So you have to ask for the actual value of the reference temperature and reference strain gauge factor close to the operating temperature that you're for. Okay, so if I'm using a strain gauge for, let's say, room temperature, okay, then 25 degrees is okay. This trend could be accepted. But if you're willing to use your strain gauge at, let's say, 1000 degrees Celsius, try to mimic the operating condition of a jet engine, then you have to ask the manufacturer for that trend, but close to the operating temperature of about 1000 degrees Celsius. Okay. Then let's see something else. This is the first effect. The second effect this is the first effect. Second effect is the change of the resistance because we are changing the operating temperature. So let's characterize this function. Okay. Now, from the physical point of view, the electrical resistance, okay, depends on the actual operating condition, temperature, through this relation. So the change of resistance is given you by gamma R delta T. Okay, in which gamma is the coefficient of variation of R with respect to the operating temperature T. Okay, and of course R is the reference resistance, and delta T is the variation change of the temperature. Now, once again, what does it mean delta T? Delta T is the change of the operating condition with respect to the reference one, which is the reference temperature. Once again, is the temperature in which the gamma coefficient is defined. Okay, so delta T is equal to T negative T0, and T0 is the one that goes together with the gamma. Okay, So you have to know what is the reference gamma or what is the operating temperature in which the value gamma is given. Okay. Typical values for the actual operating condition temperature, typical value of the gamma are those ones. So typical values of the gamma coefficients are, for example, about 40 times 10 to the negative 4 delta R over R degrees Celsius for platinum, and about 3 times 10 to negative 5, same unit of measure, for Constantine alloy material. So if you would like to set up your own strain gauge company, I can see from the website, but also from the classroom side, your eyes that are blinking money, because as you can see here, you can foresee a double use of the strain gauge. Okay, just to be explicit, let me see what happens to the change of the resistance, because I am operating those resistances at just 1 degree in difference with respect to the reference one. Okay, so let me consider to have 1 degree Celsius in difference. So delta T with respect to the reference one is just 1 degree. Okay, if we are having platinum alloy strain gauges, what we are having is the change of resistance, the corresponding change of the resistance, because of the 1 degree difference in respect to the operating temperature, is about 40 times 10 to negative 4. And therefore, what we got is the apparent strain that is induced by that, okay, is of about 800 microstrain. Okay, of course, per unit of degree Celsius, if you want to be sure. For Costantana based strain gauges, for the same change of temperature of 1 degree with respect to reference 1, we are having that this is equal to 3 to 10 to negative 5. Okay, thus the apparent strain, because of that, is equal of about 10 microstrain per unit degree Celsius. Okay, now let's compare these two results. Once again, we are using 2 different material alloys to manufacture our own strain gauges, and we are operating these strain gauges at just 1 degree above or upper or lower, okay, with respect to the reference one. As you can see, if you are using a strain gauge made by aluminum alloy, we will have a completely wrong identification of the strain, because of this 1 degree difference, 1 degree Celsius difference, we have 800, more than 800 microstrains. Remember, we are using such a strain gauge measurement to measure up to some thousand. Okay, so 800 means a lot of corruption in your data. Okay, on the contrary, if you are using Costantana based alloy, then we are having just 10 microstrain. That is not that negligible, but it is a lesser quantity than the the platinum alloy-based strain gauges. So the Costantana material is much better from the measuring point of view of strain than the platinum alloy. Also from the cost point of view, because platinum are very costly. However, and here comes the double use of the strain gauges, we can reverse the point of view. We can use such a measuring device, the strain gauge, not just to measure the strain, but just to estimate the temperature. Because platinum-based strain gauge are very sensitive to temperature. Okay, and therefore we can have a double income because we can sell strain gauges, okay, both for the strain measurement, but also for the temperature. Okay, we have to use different alloy, platinum in this case, but we can do this. And actually, if you go to your preferred reseller of such a kind transducer, they can offer you both strain and temperature measurement devices based on the resistive strain gauges as the one that we are referring to. Okay. However, for our analysis, we are using for strain gauge measurement, we are using alloys similar to the Costantana one. Okay. Question?
Yes, Professor. I didn't understand what is the point of using a platinum strain gauge.
If you see this result, okay, and if you're using a strain gauge in your actual room, okay, now, and you compare the measurement of the strain, keeping all the conditions, but just temperature. That is, if you take the measurement tonight, where hopefully there is at least 1 degree difference, okay, then the same condition will have a difference of about 800 microstrain. That is a very large difference, okay? Because we are interested in measure about 10th, 100 of microstrain. So 800 means a lot of difference, just because 1 degree. Okay, if you're using that with a 10 degrees of difference, then there is a very large amount of error. Okay, on the contrary.
Okay, and what is the point of using this gauge?
Say again, what is the point of using?
I mean, what is the benefits of making a strain gauge with platinum?
Yeah, the benefit is just to emphasize this effect. So using the strain gauge to measure the temperature field. Why that? Because with a very small variation of temperature, you have a very large change of resistance that is seen as an apparent strain. Okay, so I'll use platinum-based strain gauge to measure a temperature field instead of a strain itself. On the contrary, I will use Costantana-based strain gauges to measure the strain field, and I have to compensate the temperature effect in other ways. Okay? And that is mainly due to different value, to their corresponding different value of the gamma coefficient. Okay? That are order of magnitudes in difference.
Okay, thank you.
Okay, you're welcome. Other question?
This typical value for the gamma, like 40 cross 10 to power minus 4, R by R into degrees Celsius. So, what is the reference temperature?
Yes, we are referring to about 25 degrees. Okay, that is, these values are at that room temperature. Good question. Okay. Now, let's see the third effect. So we saw together the first effect. K is a function of temperature. Resistance, the electrical resistance, is a function of temperature. The third effect that has to be considered is the temperature effect concerning the strain. So now we are referring also to the thermal effect of your host structure. Okay, so the last effect that we have to consider is the third one, epsilon. So the strain is also a function of the temperature. Okay. Now, what we have to consider is that, once again, the measurement setup is telling me that we have to bond your strain gauge to the host structure, okay? And therefore, I am sure if the bonding device is behaving ideally, that there is no bonding effect on my measurements, okay? So that I can, let's say, consider negligible all the bonding induced effects. So what we have just to consider is the strain gauge and the host structure properties of the temperature, okay? So the condition is that, for example, we are having your host structure like this. So the test specimen, okay? And this test specimen, okay, because of the temperature field, is having a strain due to the linear thermal coefficient of expansion, okay? So, for example, what we are having is that your test specimen from here moves to, let's say, this one, okay? So this one is the new length of your test specimen, okay? What we are having now is that bonded on this structure, we are also having the strain gauge, okay? So what we are having is that from the point of view of the strain gauges, what we are having is something like this. This is the strain gauge. And then, because the original length of the strain gauge, because of the thermal effect, okay, we have also to include the effect, I am exaggerating that a little bit, of the thermal effect, okay, of your strain gauge. So that what I can say is that the strain of your strain gauge as G plus the strain induced by the thermal effect, okay, at the strain gauge level, should be equal to the strain of the test specimen. Okay? Now, just want you to remind what is the relation between the strain and the temperature field. Remember the linear coefficient of the thermal expansion. What I can say is that, generally speaking, the strain induced by the temperature field is given you by the linear coefficient of the thermal expansion. Linear coefficient of the thermal expansion. Linear because we are just measuring the 1D dimension, okay, times the change of the operating temperature. That is generally speaking, okay? So if you are looking for the effect of this temperature field into the strain field, we are looking for what I call epsilon thermal. So by referring to this equation, what I'm saying is that the unknown thermal effect on the strain is given me by the difference of the strain of the test specimen negative the strain of the strain gauge. Okay? That is, by following this information, the one that relates the strain to the linear coefficient of the thermal expansion and the previous equation, is telling me that the thermal strain is equal to the linear coefficient of thermal expansion of the test specimen negative the linear coefficient of the strain gauge times the change of temperature. Now, putting the things together with the strain gauge measurement, the change of resistance because of the operating temperature that is different with respect to the reference one, that I call that the change of the resistance in percentage, okay, because of the thermal effect, I'm operating a different, is given me by the K, that is not considered here as effect, we already considered that, strain gauge factor, times the linear coefficient of thermal expansion of the test specimen, negative the one of the strain gauge, times the change of temperature. Okay, and that is telling you the third effect, how could be evaluated. Okay.
Does that say theoretical? Like the
Thermal.
Oh, thermal.
Okay, yeah. Thermal, not thermical. Sorry, I'm going to fix it. Now, generally, although this is representative, this model is representative of the third effect, generally what we are having is putting together two different contributions. The effect of the change of reference resistance and the strain as a different operating temperature. So the change of resistance, let's say global, that takes into account two different sets, could be written as gamma plus K alpha test specimen negative alpha strain gauge times delta T. Okay, just summing up all these two different effects. Once again, I'm assuming that these effects are very small compared to the unknown measuring quantity. Everything is linear. The summation of the effects holds so that I can put just by adding the things together in order to have the effect of the two different effects together. Okay, thus my apparent strain, okay, so as a consequence of that, the apparent strain, because of the temperature that is the operating temperature that is different with respect to the reference one, is given me by this formula, gamma over K plus alpha test specimen negative alpha strain gauge times delta T. Okay, and that is your general equation. What we can see here, we are having that the induced strain because of the thermal effect, what I call the apparent strain, is a function of several parameters. Okay, gamma, K, alpha, that are the linear coefficient of the thermal expansion of the test specimen and the strain gauge itself. Okay, and then of course temperature. So what I can say is, from the measuring point of view, I would like to have as a linear function this relation between the change of operating temperature and the corresponding apparent strain. So this apparent strain is linear, is a linear function if and only if both gamma and alpha test specimen and alpha strain gauge are constant with respect to temperature. Okay? And of course, that is not always true. So we are not having a linear relation between the operating temperature and the corresponding apparent strain. Okay? So we have to do something in order to consider these different effects. What is generally done from the manufacturer point of view is giving you a third option in order to take into account of this thermal effect. And this third option is what they like to call self-compensating strain gauges with respect to temperature. They like a lot this phrase of this type of strain gauges. So the self-compensating strain gauges are those for which we can have that gamma over K plus alpha test specimen negative alpha strain gauge is practically zero. So that I can design, or better, I can use different materials, okay, and different combination between the material used to manufacture strain gauge and the material of the strain gauge, the test specimen, so that that equation is satisfied. That is, that there is no need of taking into account the temperature effect, okay, in your strain gauge measurement. Because if this is true, so that is, that is the is equal to 0 for each temperature, okay? Just because that equation is true. That is not always possible, but however, when it is, manufacturers are telling you that the strain gauge that you are going to buy is also a self-compensating strain gauge for temperature when you are using that strain gauge on aluminum alloy, for example, or on titanium alloy in that specific temperature range. And then you are happy because there's a need of further compensating procedures. Okay? By the way, yes? Yes. So it is not a matter of you. When you are buying that strain gauges, you will notice that if you're using that strain gauge on a specific material in that operating temperature range, then there's no need of compensating the temperature effect on the strain measurement. Why that? Because they made the strain gauge so that that contribution is always 0. Okay, and that is 0 if you go back here in this general formula. That means that 0 times whatever change of temperature is always 0. That is the apparent strain, the compensation that you have to make is 0, self-compensating. Okay. However, that is not always possible because you have an idea of what are the linear thermal coefficient of thermal expansion. Okay, just to remind you, if you consider the material, different material, and you consider the
excuse me, professor. So I didn't understand the meaning of self-compensating string gauge. Do you mean if epsilon apparent? I mean, we have always epsilon apparent is linear function.
No, what I'm saying is that if this is true, okay, that equation, and if you use this information to the apparent strain here, that means that the quantity in the square parenthesis is 0. And therefore, whatever is your operating temperature, the apparent strain is always 0. You made a strain gauge that compensates automatically the effect of temperature. Okay.
So you mean if the numerical relation be 0, we have apparent epsilon apparent is linear function.
No, no, not at all. It's 0.
Oh,
Because,
okay, yeah, you are right. Okay, thank you.
okay. Of course, that is 0, theoretical, whatever, but we can have the quantity 0 in a certain prescribed temperature range, not every time, everywhere.
Okay, thank you, Thomas.
And in this sense, we are calling those kind of strain gauges as self-compensating with respect to temperature. Okay, just to remind you the different values of the linear thermal coefficients, here are some values. Okay, remember we have 10 to minus 6. If we consider quartz, the values is 0.5. If you consider titanium, then we are having 9.3. Steel, mild, what we are having is 11.8. Copper, we are having 17. Aluminum alloy is about 22. Magnesium alloy, we are about 25. Epoxy resin, we are about 90. Acrylic resin, we are about 108. Okay, so as you can see, according to the different materials we use, we are having a full range of linear coefficient of the thermal expansion. Okay, and therefore you can play a little bit just to have self-compensating strain gauges. Okay, but please remember the self-compensation is possible because we are combining both the material property of the strain gauge and the material properties of the host structure. Okay, and well-defined frequency range, temperature range of operation. Okay, that could not be whatever. Okay. Generally speaking, in addition to that information, that is the chance of having self-compensating strain gauges, the operator, the manufacturer, is giving you a chart, okay, that takes into account or whatever. So you can compensate for thermal effect of in your measurement just using this chart that put the things all together without knowing any formula, just knowing the measurement as just knowing the operating temperature. And the chart is something like this. So we have x-axis, y-axis like this. So in the x-axis, we have the temperature. In the y-axis, we have the apparent strain, generally microstrain, and this is degrees Celsius. For example, we are having 0 here, once again 25 degrees. So what you're having is something, for example, like this. Okay, that is the trend, the typical value in a prescribed frequency range. Let's assume to have here negative 20 degrees and there about 150 degrees, just to have some reference temperature. Okay, the T0, that is the reference temperature, is of course here, in which at 25 degrees we are having zero apparent strain, so that is our reference temperature. Okay. So what you have to do in order to use this chart that is available from the strain gauge manufacturers is that you have to take note of the operating temperature. Once you got this information, you enter this chart with the actual readings of temperature, okay? And then you know the information of the thermal induced strain, that is the apparent strain. Once you know that, okay, you have the compensated strain, let me call it epsilon star, is given by the measure strain, the one that comes straight from your measuring device, compensated by this apparent information. Okay, so this comes from the readings, and that comes from the compensating chart. Okay, and that is the general equation that we have to take into account. Okay, so the strain gauge and the material could do whatever they like. Okay, then the manufacturer is telling you what's happening when your operating temperature is different with respect to the reference one. Which is the reference one? You can read it straight from this chart. That is, the reference one is the temperature in which the apparent strain is 0. From this chart is 25 degrees, for example. And then make your readings from the actual operation, enter this chart with that reading in terms of temperature, and your output will be the apparent strain that you have to remove to get out from the measure strain. And then you have the compensated strain. Please note that this compensation for temperature is not taking into account of delta K, that is of the change of the gauge factor because of the change of temperature. Why that? Because it is very, very small variation. Remember, we are about plus minus 1% in a very large temperature range, okay, about 100. Okay. However, if you want to compensate also for the strain gauge variation as a result of operating temperature, then you can call that once again epsilon star, same symbol but a little bit more different, as the measure strain negative the compensated the apparent strain, okay, that is just as before, and then times K over K0, okay. That is fully taking into account all the three temperature effects that we consider together. Okay. Of course, this K over K0 ratio is practically 1. So that's the reason why normal operation it is not considered at all. Okay. But if you want to be more than precise, then there is the way of taking into account that. Or if there are some special measurements for which accuracy is the most important thing, then you have to consider the opportunity. Okay. Okay, let's have a 5 minutes break. Okay, so we will recap the class, let's say 3:20. Okay.